All right, continuing on with our Chapter 8 videos, and the long-awaited section on calorimeters is here. So a calorimeter is something that allows us to measure the amount of heat that is transferred between one thing and another. Okay, so a coffee cup calorimeter is exactly what it sounds like. It's an insulated cup that is filled with water on the inside. Okay, so we can put things in the water and we can measure the temperature change of the water. Okay, and because we're controlling things, we know the mass of the water. Okay, so we can measure the temperature change. We know the mass of water. We also know the S of water. And this all works because of this whole interchange between system and surroundings. So remember earlier on in previous videos, we talked about this Q of the system equals, negative Q of the system equals Q of the surroundings. Okay, so in this situation, the surroundings are the calorimeter. Okay, and so the Q of the system could be a piece of hot metal, it could be a chemical reaction, could be any number of things. But since we know the amount of water and we know the delta T of the water, and that's the calorimeter, we can use that to find information about the thing that we put in the calorimeter. Okay, so a coffee cup calorimeter works at constant pressure, at atmospheric pressure. A bomb calorimeter is a sealed vessel. Okay, so no lid that you can easily take on and off. It gets screwed on and it's all very perfectly pressurized. And we use bomb calorimeters to measure things about food and fuels. Okay, so you'll put your sample in this little sealed thing. This is the bomb. And there's ignition wires that come out of the bomb. And so from the outside, you can trigger the combustion reaction. And then the thermometer will measure the temperature change of the surrounding water, and it works, from there on, it works pretty much like a coffee cup calorimeter. Okay, but the point is that we measure what happens to the water, and that allows us to calculate what's going on inside that bomb. Okay, so let's do a practice problem involving a calorimeter. Okay, so a chemical reaction takes place in an aqueous solution inside a coffee cup calorimeter. So basically what we have is a calorimeter full of water, and then we dump in a couple of chemicals and let a reaction take place. And it happens to be a reaction that changes the temperature of the water. So the mass of the solution is 110 grams. If the solution temperature increases by 5 degrees, how much heat has the solution absorbed? Okay, so our solution is the same as water. Okay. So we have 110 grams of water, so our mass, 110 grams. We're told that it's water, so we already know the S of the water. And we're told that the solution temperature increases by 5 degrees. Okay, so the heat absorbed by the solution is just ms delta T. All right, so we calculate that out. Q equals 110 grams times 4.184 joules per gram degrees C times 5 degrees C will give us a heat amount of 2.3 times 10 to the 3 joules. Okay, so that's how much heat was absorbed by the solution. That also means that that much heat came out of the chemical reaction taking place. Okay, because that temperature change was caused by the chemical reaction. Okay, so let's take a look at a different type of thing. So we see the words coffee cup calorimeter. Okay, that tells us that we are going to be dealing with a situation of Q system equals Q surroundings. Negative Q system equals Q of the surroundings. In the case of this problem, my Q system is the metal. Okay, and my Q surroundings is the water in the calorimeter. Okay, so we're told that we have a 10-gram piece of metal heated to 100 degrees. Okay, so let's sort of make a list here. All right, so our mass of the metal was 10 grams. And our T initial is 100 degrees. Okay, and then let's make a similar list for the water. Okay, so our coffee cup calorimeter contains 75 grams of water. And our T initial is 18 degrees because it says initially at a temperature of 18 degrees. Okay, and then after some time, the water warms to 20.28 degrees C. Okay, so guess what? The temperature of the metal is the same as the temperature of the water. All right, so remember when I was talking about this idea of thermal equilibrium, and I used the example of holding a cold rock in your hand, and after a while the rock will end up as the same temperature as your hand? Well, this is the same sort of situation. We put our piece of metal in the water, and eventually the metal's going to cool down and the water's going to warm up until they are the same temperature. Okay, so in all of these problems, your T final will be the same for the metal and the water. Okay, so our T final for the metal is also 20.28 degrees C. Okay, and then we also know our C of the water, or S of the water, excuse me, 4.184 joules per gram degrees C. Okay, so I have all the pieces I need to find Q of the water. Okay, so if we have negative Q system equals Q surroundings, that's the same thing as saying negative Q of the metal equals Q of the water. Okay, so if I find Q of the water, then I also know the Q of the metal. And what I'm looking for is the S of the metal. Okay, that's what's going to allow me to figure out which of those the metal is. All right, so since I've used up all the space here on this slide, I'm going to go down to the next slide. And I have written in the different values. And unfortunately, the aluminum's already highlighted, but we still need to go through the process of finding that answer. Okay, so we're going to solve for Q of the water first. Okay, so find Q water first. Okay, so Q equals ms delta T, and this is Q water, equals, let's see, we've got 75 grams times 4.184 joules per gram degrees C, times, and I'm running out of room here, final temperature was 20.28 minus initial temperature, which was 18. All right, so remember when I said that the delta T part is a sig fig trap? When I do that subtraction, I get 20.28 degrees. But it's a subtraction problem, so I have to track at the first decimal place because that 18.0 only has one decimal place. All right, so my Q water is going to come out to be 7.1546, tracking at the second sig fig, times 10 to the 2 joules. Okay, so that means that Q metal is just negative of that. because of this relationship here, that negative Q metal equals Q water. So if Q water is positive 7.1, then Q metal is negative 7.1. Right, so I want to solve for S. Now I have the Q, the M, and the delta T for the metal. So S equals Q the metal over M delta T. Right, and boy, are we running out of room here. So negative 7.1546, and I'm keeping all those digits, times 10 to the 2 joules over our mass of the metal was 10 grams, and our delta T was 20.28 minus 100. Okay, our initial temperature was 100, our final temperature was 20.28. Right, so that temperature is going to come out to be a negative value, and then I've got a negative on top, so that gives me a positive value for my answer. So it comes out to be 0.897 joules per gram degrees C. Right, we find that that is the aluminum. All right, so let's do another one of these. I know probably right now your head's swimming a little bit. All right, so a chemist conducts a calorimetry experiment on an unknown metal. The mass of the sample is 52.4 grams. Okay, that's the metal mass. And the chemist heats the metal to 100 degrees and then places it in a coffee cup calorimeter containing 95.4 grams of water. Okay, so that's the mass of the water. And then the temperature of the water rises from 21.9 to 23.2 degrees Celsius. So what is the heat change for the water? Okay, so easy enough to find that. This Q equals ms delta T for the water, because we have mass, we have delta T, and we already know S. Right, so here's another situation for it. Negative Q metal equals Q water. Right, so our heat change for the water, we just solve for Q. So it's 95.4 grams of water times S of the water times our delta T for the water. Final is 23.2 minus 21.9. So our delta T for our Q, our Q for the water comes out to be 518.899. All right, and remember we're tracking at the second sig fig because the temperature difference ends up giving us only 2 sig figs. All right, so thinking about, so that's our Q of the water. All right, so if Q of the water is 518, then our Q of the metal is just negative of that. Okay, so this Q water equals negative Q metal is always going to be the relationship. Okay, or Q reaction. Negative Q reaction equals Q water. Like whatever we're comparing water to, the other thing is just the opposite sign. So finding the specific heat of the metal is just like in the previous problem. So S equals Q over M delta T. So just rearranging the Q equals ms delta T equation. All right, so our mass of the metal is the 52.4. Our T final is the same as the T final for the water, which is 23.2. So we have negative 518.899 at the second sig fig, divided by our mass of the metal, 52.4 grams, and our temperature change, 23.2 minus 100. And that's degrees C. So we'll find that the specific heat of the metal is 0.129 joules per gram degrees C. Okay, so we're going to go ahead and stop this video right here, and we'll pick it up with our last topic, which is heat energy and chemical reactions.